Ever wonder what holds our world up? I mean, really think about it. Every single skyscraper, every bridge, every home. It's in this constant, silent battle. Today, we're going to pull back the curtain on the hidden science that keeps all of our buildings standing. And it's all thanks to this one crucial document you've probably never even heard of. So let's get into it.
So let's just kick things off with a question. I want you to forget about earthquakes and wind and floods for just a minute. What do you think is the single most dangerous, most relentless force that every single structure has to fight against? 24 hours a day, 7 days a week, no exceptions.
Well, the answer is kind of surprising in its simplicity. It's the building's own weight. Seriously, from the very second it's built to the moment it comes down, a building's biggest and most constant enemy is itself.
So you have this constant pull of gravity, right? It creates this immense, unending pressure. And to understand how engineers actually fight back against this force, we first have to really get a handle on this invisible enemy.
You see, in the world of engineering, this force has a name. They call it the dead load. It's exactly what it sounds like, the fixed, permanent weight of the structure itself. Think of the concrete, the steel, the bricks, the glass, all of it. It never goes away. It's the baseline force that the entire design has to overcome, day in and day out.
So how on earth do you design for a force that you can't even see, but is always there? Well, you need a rule book. A rule book for reality. And for engineers in India, that rule book is the Indian Standard IS 875 Part-1. It's basically the ultimate guide for calculating these dead loads.
And this gets right to the heart of the engineer's dilemma. It's this incredibly fine line they have to walk. If you underestimate the dead load, well, you under-engineer the building, and you risk a catastrophic failure. But if you overestimate it, you over-engineer it. And that leads to what the code itself calls a wastage of materials and, of course, money.
And that's where this code is such a game changer. It provides the exact, standardized data that engineers need to find that perfect sweet spot, turning a dangerous guessing game into a precise science. It's all about hitting that target of an efficient and safe design.
And seriously, when you actually open this thing up, AS 875 isn't just some boring old rulebook. It's more like a fascinating encyclopedia of weight. The level of detail in here is just incredible. So let's dive into a few examples, shall we?
Okay, take something as simple as a brick. You'd think a brick is a brick, right? Nope. The code doesn't just list one weight for brick. It actually distinguishes between common burnt clay bricks and the heavier engineering bricks. Now you might be asking, why go into that much detail? Well, because that tiny difference in weight when you multiply it by millions of bricks in a huge building could be the difference between a safe structure and a very unsafe one.
All right, here's another one that seems super simple but has these huge implications. The code actually specifies different weights for sand depending on one little thing. Is it wet or is it dry? I mean, come on, why would that even matter?
Well, the reason is pretty straightforward. Water is heavy. As you can see here, the weight of sand can jump by almost 25% when it's wet. So if an engineer doesn't account for the moisture that sand is going to absorb out in the real world, they're dangerously underestimating the total dead load. Now let's talk about the really heavy hitters. This number right here, 24.8 kilonewtons per cubic meter, is the unit weight for reinforced concrete with about 2% steel. Now, I know, that unit sounds super technical, but to put it in perspective, a single cubic meter of this stuff weighs about 2,500 kilograms. That's like 2 small cars. Now just imagine thousands of those stacked on top of each other in a skyscraper.
But here's what's so cool about this code. It's not just about these massive, heavy things. It's also about incredible precision. Look at this tiny number. This represents the weight of a single 6.5 millimeter thick sheet of glass. From the heaviest concrete core to the lightest glass skin, literally every single component is meticulously accounted for.
But wait, there's more. The code doesn't just stop at the raw materials. It goes way further to build a complete picture of a building's weight, from its assembled parts to the very things we decide to put inside it.
See, a building isn't just a pile of bricks and sand, right? It's made of these complex systems. So the code provides weights for the whole shebang: ceilings, flooring, roofing, even specific kinds of walls and damp proofing. It's accounting for the weight of the building as it will actually exist, not just as a collection of ingredients.
Okay, but what about after the building is done? For places like warehouses, libraries, or factories, the weight of all the stuff stored inside can be massive, and the structure has to be ready to handle it from day one.
And this is where the scope of this document just gets
Well, mind-blowing. There's an entire section that lists the weights for hundreds of different stored materials, everything from corn and chemicals to heavy metals and paper. This is what allows engineers to design these specialized buildings, like a warehouse or a library, so they can safely handle whatever they're built to hold.
So, after going deep into all these details, the bricks, the sand, the concrete, let's just zoom back out for a second. At the end of the day, all of these numbers and tables and clauses, they all point to one single vital goal: building a safer world for all of us. The logic here is just so clear and powerful. First, you identify every single material and component. Second, you use IS 875 to calculate their total weight, the dead load. Third, you design a structure strong enough to support all of that. And the result? You get a building that achieves maximum safety with minimum waste. It's brilliant.
You know what? You don't even have to take my word for it. This quote from the document's own foreword just sums it up perfectly. The goal isn't just safety. It's about intelligent, efficient safety. It's about knowing exactly what you're up against and engineering the perfect solution.
And that's really the key takeaway here. Every single time you walk into a building and feel safe, you are benefiting from this unseen science. The meticulous, incredibly detailed work that's written down in documents like NIS 875 is the invisible foundation that allows our entire modern world to stand tall. Which, of course, leaves us with one last big question to chew on. We spent a century cataloging the weight of concrete, steel, and glass. We've mastered it. But what will the buildings of tomorrow be made of? Graphene? Maybe carbon fiber? Self-healing biomaterials? And who are the people who are going to write their rulebook?